showed up in the morning. So it's very nice that alcohol in Copenhagen is very expensive. So everyone's very fresh, and I'm very relieved. And just to start the session, yesterday we had a couple of things that you still needed to download. I am not screen sharing with Zoom, so thank you, Daniel. Let me share the screen. Okay, so yesterday we asked you to download some files, and this is just a summary. You don't have to scan it. If you think you managed to download everything, you don't have to scan it. It's just for everyone also online who might not have gotten the email or something. So every one of you should have a folder of like 88 files or something, like MZmine files of different samples of your group. So there was example, and then I think 2 groups. Then there is the MZmine version that we just pushed yesterday, because we like to be playing it kind of last minute. So we pushed a new version 3.9.0. And if you have any previous version and you're not able to download it now in the first session and you're not able to install it, that's going to be totally fine. It's going to work like 99.9%. But we just fixed a few things and made some new features even that you're going to show that we're going to show on the screen. Then there's the Mass Bank of North America LCMS mass positive library, so a Spectral reference library. We mostly use this library because it's kind of medium size, is like 90,000 spectra, so it's kind of small. So it's going to run on like all the laptops quite easily. And if you have GMPS downloaded, if you have any other libraries, you can also just plug them in and use them. We do want to highlight though, because everyone's kind of going to try out and set some other parameters. And there's some downstream analysis that we're going to do the next days, that we also put some files on the GitHub. And maybe I should add the link later to that. So later we have to go to GitHub and download the exact files. Yeah, so just to make sure that you have the same output files, everyone, the same group, so that we can use Sirius, that we can use MatchMS and MS2LDA, GMPS, all of those tools. Yeah. Typically, if you have the parameters, you can just rerun and you should get the same output, but we just want to make sure that everyone's on the same page. Okay. So one thing, just a self-plug for MZmine, we're going to have a 20-year anniversary soon. And so there's going to be next year in April, it's going to be 20 years MZmine, and we're going to have a nice workshops, maybe not as nice as here, but we try to also deliver. And this is from like 2021, where also like many of like Sirius and Daniel and like so many different teams came together. And so we're also going to try to put together like a nice program, and you can look out for it and on our Twitter and also on other social media to try to find us. And so today is going to be like the introduction to data processing, and we're going to use MZmine today to extract mass spectrometry features. We're going to explain and discuss what that is, and then also later send them to other tools that then can make use of the results and give us more insights into annotations and how the chemicals in our samples are connected. And so for this, kind of like a very broad overview, we have MZmine really just doing like spectral processing, extracting of features, and then also alignment across samples so that you can do statistical analysis later. And then GMPS, you can kind of see like molecular networking, and we're going to discuss it today a little bit, but then also tomorrow is we look at the fragmentation pattern similarity. So there's fragmentation patterns, we already heard about it. So we apply energy to structures, we cleave them down, we measure the fragmentation spectra and look at the similarity to map kind of like the chemical space. Yeah, so what does that mean? If the fragmentation spectra are similar, we hope that the structures of those molecules are also similar. Yeah, and very often it's the case, and we're going to show some examples of that. And MAST, I'm actually not sure if we really going to cover it. Yeah, right. Maybe there's going to be some time, but just for you to be aware, like usually you run on your own data sets, But if some of you already upload your data to some of the repositories, like Justin introduced, Metabolites, Massive, and Metabolomics Workbench, we're able to query this data with individual spectra. So maybe you're already working on isolating some compound and you've got the MS2 spectra, it looks very interesting. You can match that one MS2 spectrum against all MS2 spectra in the public domain. And then you might be seeing that it might be something microbe-derived, food-derived, maybe it's from environmental samples. So someone already detected it. And that might help you, like, guide you in further analysis. And to jump into mass spectrometry data to kind of give you an overview of what we're dealing with, at least in chromatography mass spectrometry, there is, like here in LCMS, we have two major dimensions of separation. There's the retention time here on the one axis, and then MZ, it's kind of blurry, and MZ on the other axis. And if we just take a slice of that, we get the mass spectrum on the left side. And the mass spectrum is really the raw data that we measure. Yeah, it's really like the detector that we're using. Yeah. Of course, depends on the detector if you're really getting the spectrum like that, or if it's produced already by heavy processing internally. But if we now want to find the peaks, so we really want to get the chromatograms and we want to get like chromatographically separated peaks, we have to find the same mass to charge ratio and then connect the dots from like measurement to measurement. Yeah, so each retention time we have a full scan, usually with high resolution mass spectrometry, and then we connect it to features. And we saw this slide before. Just want to highlight that LC and GC, very much the same, like the data structure is basically completely the same. We have spectra and we extract chromatograms, and we have in imaging, we have spectra and we extract images. So we find the same mass to charge ratio across the whole spatial distribution. And now, like, one very important thing that we always have to deal with is centroiding. So very often you might be acquiring the data in profile mode. There's some instruments that even always acquire in centroid mode, because otherwise they can't handle the amount of data that they have to push. Like if you have really fast scanning TOF instruments, sometimes they always acquire in centroid. So internally, they already have to apply some peak picking. And peak picking, we know it from MZmine, like there's always going to be something that goes wrong. Yeah, so you always have to remind yourself it's not necessarily always that we are at the state right now that it's perfect. So there's always going to be improvement in the future. So what we typically say is keep your raw data if you have it, and then also during the conversion, convert it to Centroid MZML. That's like the latest, at least open source format that most of the tools also use as an input. Yeah. So for me, I always convert it directly after acquisition for thermal raw data. It's very easy with the thermal raw file parser. They already come with like all the different standard settings. There's also MSConvert, and you can also apply centroiding there and use the vendor algorithms. So, and we do have some guidelines on MZmine documentation and also on the GMPS documentation. And I just want to highlight that there's like so many things that can go wrong, right? So we had some things where some TOF data from one vendor was basically centroided and also recalibrated, and then the raw data is recalibrated, but the metadata was not. Yeah, so if we had an MS2 scan, we usually select an ion, and that was kind of linked to the MS1 spectrum. And now if we just recalibrate the data, but we don't recalibrate what the precursor MZ says, it's very hard to connect the dots and to connect everything, right? So, and this was really like during the MZML conversion. And there's some workarounds and some fixes, but that's why, like in the documentation, if you find that with the vendor that you're using, like the data that you're getting, you have some struggles and you find some solution, maybe just put it in our documentation or like any documentation that you can find so that people can at least find it, right? And also we're going to look into mass spectrometry data. So we're also going to find a lot of artifacts also, but I would not call those things artifacts. So we have the isotope patterns and we have the different adducts. And to me, it's very important because it kind of also proves the point that we have something that has natural 13C pattern, for example, or that we have something where we have like a multitude of signals telling us the same story, right? So if I see M plus H and M plus sodium, I'm kind of sure that it's really like M. If I just see one signal, it could also be like an in-source fragment. So we might be just baking off the sugar and caramelizing our compounds in the in-source, right? So that's not going to be very nice. And we're going to think that we found something super nice. And the same is true for like dimers. So sometimes things just like stack together. So you have some multimers forming in-source. So two molecules stacking together, and then one sodium, one hydrogen, like proton. And you think you found something new, but it has the same retention time like all the other ions. And we're going to look into that. And just a very short video. This is the like interface of MZmine. And we're going to go through the data in here. Stefan is going to guide you through. And we're going to see how like the data is actually connected, like the chromatograms on the left and the spectra on the right. And with this, I would like to come to MZmine, and I have to stress that this is only one of the like community projects. There's a lot of other projects that even do similar things like feature finding, annotation, and all those sorts of things. And I think in this summer school, you're already going to learn many of them, and it's kind of overwhelming. Like many people are overwhelmed by just switching from MZmine 2 to MZmine 3, and I can understand them. But yeah, there's going to be like very many tools, and you have the chance to talk to developers of MatchMS and Sirius and so many, and MS2LDA and so many different tools. So really take advantage of that, but then also exchange with other people. Like, what kind of tools do you use, except for the ones that we see here, right? Because there's XCMS that is an R. It's a very nice tool. There's R for mass spectrometry, actively being developed. So if you're more in R, you know, sometimes just try it out. There's MS-Dial for data-independent data, very nice, and lipids. And so there's a lot of tools that you could try, but yeah, we're going to focus now on the ones that we know best, right? And so for MZmine, it's been in development for 20 years. Tomasz Pluska was really like a driving factor when he modularized the whole project and then published MZmine 2. And since then, we have, now it's even more like 53 like active contributors over the whole like, time course. And yeah, like many different features being added by many different institutions. Yeah, so it's not just like one person who started a project and then like Tomasz always kept like very openly, so people could just come in, add a new module that might just be interesting to just you or maybe your lab, right? But we were very like open to just say, yeah, like if it doesn't break anything else, like why should not we like host it in MZmine, right? And so if anyone is programming, this is a Java tool. And that's going to sound scary nowadays because Python and R is all the data analysis and everything now. But it's, if you can code, it's not different. Like it's the same. And we have some infrastructure in there. So it's very easy to pull the user parameters and then also to parallelize the processing and make it run really fast. Yeah. So if you want, we have in the documentation some guidelines how to start. And you can always reach out to us. And so getting more into the data now. So of course we have to import data. There's a few formats that we support. Mostly I would say use MZML for everything. And then maybe for timsTOF data, they have a native format that we also support because IMS data just gets massive when you convert it. Yeah. Then we do spectral processing. And today we're actually only going to do centroiding is already done. So the files that you downloaded are already centroided with the vendor algorithm that is supported by MS Convert in this case. And we're only going to apply a threshold. Yeah, so we're only going to apply denoising basically to the scan. Then we're going to try to find the same mass to charge ratios across the whole retention time range. So across scans. And we build extracted ion chromatograms. And maybe I can even put a pointer. I told that to myself and then I forgot. Doesn't work. Oh, okay. Never done that before. Okay, okay, now it works. So, so yeah, we have the extracted ion chromatograms first, and then in the second step, we need to find the valleys and find the peaks. Yeah, so we need to apply some peak constraints to split chromatograms into separate features. And what is a feature to us? It's just an MZ, so it's just a mass to charge ratio, and it doesn't matter if it's like LC or imaging or whatever. It's just a mass to charge ratio, but it has much more properties. Yeah, so there might be the retention time index, and MS2 spectra and other properties attached to it. Yeah. And then one of the most important steps and crucial steps is the alignment. Yeah, because we usually have a larger sample set, and we need to kind of find the same peaks in retention time dimension, MZ, across all samples. And there might be multiple chances how to align a sample set. So we really have to take care of this step. And especially if we try to find everything in the steps before, we're also going to end up producing a feature list of like 100,000 of features. And then we want to align it over thousands of samples. And it's a quadratic operation. Yeah, so it's not going to perform linearly. So if you expand on both numbers, like the number of samples and the number of features that you detect in all the samples, it's going to run for a very long time and maybe even run out of memory. And because MZmine is very modular, it's very easy, or it was very easy for us to implement some new modules to also support ion mobility spectrometry. And this was mostly due to great work that Steffen did. So he programmed all the modules to then go from LC-MS data or even imaging MS data into the next dimension. We will have one more separation dimension. Not going to cover it too much in this workshop, but hopefully if we have some time at the end, we're going to show a few slides, and maybe we can just talk about like what IMS might bring to the game of metabolomics. And then there's ion density molecular networking and other modules that we added to MZmine for annotation. So you can do some more steps that are optional in MZmine. And then we can export everything to GMPS for molecular networking and many more tools, to series for compound annotation, and also for getting compound classes. And then also, of course, to do statistical analysis. And for statistical analysis, there is many different tools, but especially from last year's summer school, there was also the Hitchhiker's Guide to Statistical Analysis and Feature-Based Molecular Networking, something like that. And so we have some Python R and Streamlit app. And so we put together as a team, like all the different resources and scripts that we typically use. And very much by like Madeline, Philip, and Abzer, and many other people. And once we have set up the whole pipeline, so the other one kind of looked kind of easy still. Now we put together the whole pipeline with like all the optional steps and IMS and everything. It might look kind of scary, and we don't have to set up everything today. We're going to kind of take a short track. But the nice thing is that everything is modular, so you can just send this configuration that we do. You can save it, you can send it to collaborator, you can also publish it with your paper. So if you already have a GitHub repository, for example, where you code your figures, or you have Zenodo, or you put anything anywhere, you can just drop the batch file with it, and then people can directly reproduce. There's the MZmine version in it. It's always good to still like define it, but there's the MZmine version, and also like all the steps have a version, so people can really reproduce it. And then for the development of the last year, so MZmine 3, we released like March 1.5 years ago or something. And we already developed it for a long time. Maybe some people were waiting and were like, why is there no new release in MZmine 2? And so if any one of you is still using MZmine 2, I tried it out like 1 year ago, and it was such a pain to set anything up. And it used to be like, I joined the project, and it used to be like the super user-friendly tool and so on. But I think MZmine 3 now, we made a huge jump, like how like user interaction is managed, and also in terms of speed and sample throughput. So this was really like one test which we did. We had like 250 DOM samples, so dissolved organic matter, very complex samples, and we ran it on this laptop, and it was like way faster to process. And so just to wrap up the processing in MZmine, we're going to produce a feature list, and it's going to look somewhat similar to the one on the right side, where we're going to have some charts and to look at the quality of the peak picking and maybe alignment. Then we have some other columns here with annotations and parameters that are being calculated, but Stefan is going to guide you through here. And just because it's very important, I just want to reiterate, you know those slides already, right? But with fragmentation mass spectrometry, like we select one ion. Yeah, so we first need to do an MS1 pre-scan. Like we need to scan all the ions. Then usually at DDA, we select the top 5 or something ions. We have to isolate it in the quadrupole or in an ion trap. And then we measure it and we get the intensities of the different fragment ions. And Corinna already said that it's very important to look at the molecule and kind of also see where's the charge in the beginning. It's not very obvious very often because in gas phase, ionization works very differently than we expect it to do. And so it's very important to just expect the charge somewhere, and then it's going to move around and it's going to trigger some fragmentations. Yeah, and so only the charged ions we can see, and then everything else is going to be neutral losses. And so if you look at a structure, we can then see like where it breaks down. And so if we now combine that with the feature table, we're going to see that some of the features, and this is completely made up. So here you have like overlaid chromatograms of multiple samples, so it looks very complex. And then there's with the stars, we could mark like all the features where we have MSMS, so fragmentation spectra triggered. For like most of the downstream tools, this is very important because MSMS spectra is kind of a must for compound annotation. And we're going to look into this now, but just for the feature table again, like on the left side, we have feature ID, which is going to be important to align all the results. That's why we download the files that we already processed, so that later with Series and MZmine and all the other tools, MS2LEA, we can combine the results later. On the right side, we have the samples. And so for each sample, we did feature detection. So we're going to have also MZ, retention time, intensity, like height and area, and more things. And they're going to be averaged on the left side. Yeah, so we always have like the row giving us the average, and then on the right side, we can have all the feature information, like per sample. And you can see, I forgot to actually exchange here, like the level scheme, but it's also kind of good because yesterday, Corinna showed you 4 levels. And like, I would say Metabolomics field is still like not, like standardization is kind of lacking. So I'm not a like, I don't say like we should standardize too much, because then also it kind of hampers development sometimes. Like, hey, you have to use this method, you have to report it this way. Can also sometimes hamper development. But at least for the annotations, it's very unclear sometimes to like what level you have to annotate. But if you send something for review, they're definitely going to come back and be like, hey, like you have to put some levels to the annotations. Yeah. So, and we would highlight that it's mostly about just giving proof for what you claim, right? So if you measure the reference standard and you got the retention time and you got, they always say like 2 orthogonal dimensions. So retention time, mass to charge ratio, and then also the fragmentation spectra matched to a reference standard. It's a level 1, right? So we have a direct match on like multiple properties. Then we have here is like the 5-level scheme of Szymanski et al., which is more from like the environmental chemistry. And we have the 4 levels, which is more from the metabolomic society. And the other levels are pretty similar. So it's like 2 is mostly like probable annotation, or they also say putative annotation. Then we have the 3, which is kind of the same, and then the 4 like molecular formula. And I just want to stretch here that I'm usually using the MSI because you have like 1, basically multiple orthogonal properties give you a match. 2, you have a match, but you don't have the reference compound, so you cannot really compare multiple properties, and you're just matching to reference databases. And then typically you have 3 when it is more like a class match in MSI now. And the class match really means like, I'm not sure, for example, for lipids, I know it's a phosphocholine, you know, I know it's some phospholipid, or, you know, you maybe know the head group and so on. So you can say it's this class, yeah? But still, like in both of those schemes, it's very hard to say, like, where do in silico tools fit in, like series, for example. It's very hard because they are not really covered by the examples that they have. And so we would just say, provide a table and do as good as you can, and just say, okay, we had a reference compound for this one, we did not for this one. We do have MS2 spectral matching, we match the retention time to databases and so on. And now just like to scheme up 2 people, like 2 analysis schemes also. So some people might go and just identify everything. Yeah, so they go in and they do the identification on like all the features that they get, and then they try to derive some knowledge from there. Or some people first export everything and do statistical analysis, and then try to find significant features, right? I personally think the tools are ready to be used and to identify the whole data set very often. And then later we can still do statistical analysis, and we can then combine everything on molecular networking, like we're going to see later, and also put like significance and the annotations together. Because sometimes, you know, you might find a metabolite of something that is like filtered out as being insignificant, but this insignificant compound was actually annotated. And then you might be losing some information if you just filter out all insignificant compounds. And for annotation, just want to say that there's really like just annotating based on molecular formula prediction. So just using the accurate mass to charge ratio, even if you can push it down to like 1 ppm or 2 ppm, is not really the way to go. Like nowadays we have spectral libraries, we have series and other tools that can help you. And we can see here that just by looking for CHNOPS, which is a very limited alphabet of atoms, we can already like predict 670 formulas for this one mass to charge ratio. We can of course limit it more, and we can also say there's only specific ways how we can combine carbon and oxygen and heteroatoms and hydrogen, right? So this is in those like 7 golden rules, heuristics. And we can also look in general databases, which some people do, right? They just say, okay, it should be in PubChem, right? But should it? Should it really be in PubChem? PubChem is not complete. Yeah, so maybe you got the one golden ticket and you found a compound that is not even in PubChem. And of course, not even in bio databases, right? Because they have a higher bar of accepting compounds in. And so it's very much like a good hint if you find something that is biological and you're working on a biological system, but it's not, I would not really use it so much for exclusion. And to again go for this, like how can we actually put together molecular formulas? If we're gonna look at mass spectra, to me, the first thing I always do is look at the MZ and also look at the mass defect. And mass defect is very important in high resolution mass spectrometry. So you zoom into the signal and you see it's a 200.8. Does that make any sense? Like how can we actually fit so many hydrogen onto carbons that we get to like 0.8? Okay, maybe there's like a chlorine or bromide or whatever, but then the mass should be higher, right? So it's very much like you can look at the mass defect and at the charge of the isotope pattern that you can see, and then you can directly say this is trash. Like I don't even try to annotate it. Yeah. And you can see it here. We plotted didn't even write it down. So we plotted below 200 MZ. And in this range, very much like the first hump on the left side should be all like saturated and unsaturated compounds with like a lot of hydrogens driving the mass effect up. And then on the minus, I would say, yeah, so like 0.9 point something, on the right side, you have all the ones that have like a very little hydrogen and then a lot of heteroatoms. Yeah. And in the center, most likely at MZ200, it's just doubly charged ions. Yeah, so there's no other way to get to 0.5 in like 200 MZ. And so if we like combine everything, we said that we need MS2 Spectral for annotation. And of course, the first thing that we would do is annotate manually. And I really recommend that to people sometimes, because it's nice to get an idea about fragmentation that can happen in mass spectrometry. And tools actually can also guide you there. So interface in series, for example, can show you what is like a probable fragment ion that was produced there, or like what kind of part of the structure might correspond to signals. And if you do this manually, you can see that for this structure, for example, there's an NH2 and OH, so just an exchange here. And it's already producing like two distinct fragment ions that we can see, and maybe even some neutral losses that I didn't cover here, but two distinct fragment ions that really point out this NH2OH exchange. And then again, for the positive negative mode discussion, I would say most people, at least depending on the chemicals that you study, acquire positive mode data. And we can already see it for like tool development. There's a lot more reference data in positive mode. So tools like Sirius and so on, like tools usually predict better on positive mode, I would say, right? Slightly, he says. Okay. So a bit more. But yeah, but I want to say that for your compounds, if you don't see anything in positive mode, maybe it's time to change to negative mode and try it out. And especially for lipids, we can already see that for phospholipids, it very much depends on the head group and so on, but the chains, they're acids, right? So it's very much like easier to retain the negative charge. It's not going to be there from the start, but it's going to be easy to like rearrange and do some fragmentation and then cleave off the side chains in negative mode, and then also see them in the negative mode spectrum. And in positive mode, we don't see them really. We do see some like neutral losses of them, but we don't see the fragments very often. And then one like standard method that we typically use is mass spectral library matching. And here it's very important that we don't have much reference data. Like there's so many labs in the world acquiring mass spectra over and over again. But it's still like we try to make the bar like very low so that people actually submit spectra to mass bank, to GMPS and so on. But it's still maybe, you know, not easy enough, or maybe there's not an incentive or something to really like submit data, because the data is like rising, like we have more and more, but it's still not there that we can really use it even better for like machine learning and so on. So if you have some libraries sitting at home, compound libraries or already acquired data, we can help you. And Corinna is working on a project really pulling the strings together to have a like automated workflow library creation. And you can just talk to her, and maybe if we have time, we can show it later. Because I think it's very important, like how do I extract from my reference compound, how can I extract data and maybe also send it to the public domain. But just describing what we see here is we usually have the reference spectrum on the bottom here. So this is and we have some metadata. So we can see this one was acquired with a thermo, Q executive HF. In MS2 mode, and collision energy is even listed here. And we can also reach out to the submitter of the data, because maybe they still have the compound, right? So making those things public can also help you later like be found and also find other people that might be working with the same compounds. And then on the top, we have experimental spectra, and then usually in those mirror matches, you see all the signals that are matched, and then cosine similarity, and there's also other scores being developed, and we have the developers actually here also, and so MS2 Deep Score, Spectrovac, so there's other scores that we might be seeing in the MZmine session later. And for GCMS, because GC, AEMS at least, so electron impact, is a high energy ionization. Yeah, so we collide with electrons and we fragment the whole structure. And because of that, we typically don't have information on the precursor ion. So we don't really know what we fragmented. But then because it's so much standardized, like it's been standardized from like the 70s or something, and we can really match to fragmentation spectra that were being acquired like 20 years ago, and we still get like mostly a perfect match. The thing is though, like we see already is like a fatty acyl methyl ester, because for GC we kind of have to make it non-polar, and maybe it's an ethyl ester, right? I mean, I know this, like most likely this is just because we needed to make it like go into the gas phase, but in the matching, it's sometimes just slight changes when we elongate like the chain, or if we also make some changes, small slight changes on the structure. Yeah, so sometimes it's good that in LCMS at least we have the precursor MC. And with this, we come to the MZmine hands-on session, and I don't even know what the timing is, but maybe we can have some questions before, right? Do you have any questions? So in the MZmine hands-on, we also have time for questions. We're going to go through data and then set up all the processing and get some results first. But do you have any questions already for data conversion, data handling, any that we discussed, annotation? Yeah.
Are there any situations where you would prefer XCMS over MZmine, or?
Okay, the question was if I would prefer XCMS over MZmine at any situation. I would definitely prefer it if I was already in an R environment. If I already have scripts to do like downstream processing, and I already have someone already set something up, right? And but generally, I think it's very important to just try out the different tools. And I know that they are like very actively developing it. And if you're already proficient with R, it's very nice because you're already in that system, right? It's very easy to push data around to do the downstream statistical analysis. And with MZmine, we're very much not focusing on statistics because we know that R and Python are just very flexible and very easy to use. So we rather pipe the like export the results and then pipe them into other tools. Yeah, and then maybe import back the results. Yeah. And the same is true for Python packages. There's a lot of Python packages that do like all sorts of processing, PyOpenMS, MatchMS. There's many packages that you can use. And if you're already in the Python universe, it's very easy to plug them in. And I also use it to clean up data, to extract data, to convert stuff. I also use it. So it's very much, yeah, you find the tools that are useful for the job. Okay. Okay. What was it? The resolution. Agilent QTOFs. Okay, so that's two questions. Agilent QTOFs. My answer is always that like the vendors should support open data. And if I would buy an instrument, I would always ask for it, and they would always tell you that they support open data, that they support converting to MZmine. But maybe also just search on like some of the tools, like, hey, do you have problems with Agilent, with Sykes, with Waters, with Bruker, and so on, right? Just search on MZmine, and you're gonna find some of the names popping up more often, and then maybe that's old, right? Maybe that was like a couple of years ago, but at least this is something to ask them, because yeah, like open data is not supported the same way by like all the vendors. Yeah. And the second one was if the resolution is high enough to determine exact mass. I mean, how exact? I mean, first of all, like I would say exact mass is the calculated one, so it's really exact, right? And we usually do like accurate mass, and you can always do so for me, like accurate mass is the one that you measured, and you can always do recalibration. So you can have like an internal calibrant at each scan, and some vendors really do that already internally. So yeah, I think that should work. Stefan also nods, so. Yeah, the hope processing data of both polarities. Yeah, you can already process data of both polarities, but so far we don't really make it so easy. Like we don't have a out-of-the-box solution to directly merge like positive negative mode. And some other people also want to merge other types of analyses, right? It's not only positive negative mode. Might be that you do MS1 only to get like really nice peak shapes, and then you have like QCs or like pooled samples where you really do like deep scanning MS2. So you inject multiple times a pooled sample and try to acquire all the MS2s and then merge it. So those things like we might be able in the future to support better. So yeah, is there an equivalent algorithm to SendWave available in MZmine? There was SendWave, so there was like an R integration of in MZmine, but personally, like really like integration between the languages is sometimes a bit tricky because we have to then support like kind of the versioning and the libraries, and like all of them run in virtual environments. So it's kind of hard to set up. And I personally don't think that there's much of a difference using SendWave or the ADAP chromatogram builder and also like the mass detection that we have there. I think that should work all. Then there's if there's like DDA and DIA support. So we did not talk about it. So MZmine was never really strong on data-independent acquisition, but we do implement more of these modules, especially Stefan did. So we do want to support more data-independent acquisition modes. Currently, it's still like, I would say, just try out the tools that are very good for that. So try out MSDial, try out MZmine, and just kind of compare what you get, right? It's very hard to tell which one is the best tool for that, but traditionally, they had a very strong focus on that. So I think their methods work very nicely for like, especially like all the waters data that very often is acquired in data independent acquisition. They might just have really specialized also on that. Then there's a lot of questions coming. Oh my God. And maybe we can just also say, I know some people are very, they really want to get into data independent acquisition and all ion fragmentation and so on. I personally don't think it's so useful for metabolomics. I think it's a bit dependent on like the compounds and on the structures and everything that you're looking at and how complex your samples are. I know that some people are very interested, especially with the new instruments that scan very fast. But personally, I think just having smarter algorithms that kind of like keep track of, oh, wait, this one I already saw, or maybe I tried to fragment, but the energy was not high enough. So maybe next time I just apply some more energy. So of course, this is all processing that needs to happen. But I think those kind of things, at least to me, are more like making sense for the future. But let's see, I mean, at least in the proteomics field, and yeah, it's applied with great success already. So maybe it also swaps over to metabolomics. Okay, so how to select and optimize settings, I'm not going to go into because we're going to do it today in the session, and Stefan is going to guide you through that. And maybe we can, for now, just someone can tell me how much time we have and if we should start the processing, right? So yeah, we're going to answer more of those questions later. Yeah, but most of them, I think, yeah, like if anyone knows, you can also answer those questions. And most of them, I think we're going to answer also by just going through the processing.
If there's something important, then we can do it now. Or